We are attempting the impossible, building a star on Earth. Nuclear fusion, not in space, not in science fiction, but inside a machine right here on this planet, because the future is starving. AI data centers and modern economies are devouring power at a rate fossil fuels can't sustain. We are racing toward a thermodynamic wall. And physics does not negotiate. It only sets the terms extreme temperature, crushing density, and enough time to keep a plasma from tearing itself apart. We've already triggered ignition in the lab. For a split second it worked. But a power plant is not a split second. It's a machine that must survive, repeat, and pay its own energy bill. So here's the real question. Which law of physics stops us first? To answer that, we must look at the silence of the night sky, not as an emptiness, but as a warning. There is a hypothesis that civilizations hit a thermodynamic bottleneck, a point where their energy needs outpace their planetary resources. We are currently fueling 21st century artificial intelligence with 19th century fossil combustion. We are hitting that wall. To break through, we must master the equation of the gods, the Lawson Criterion. In 1955, physicist John Lawson realized that fusion ignition depends on the product of three fundamental variables: density and temperature T, and energy confinement time tau. It is a cosmic balancing act. To achieve a net energy gain, the product of these three must exceed a critical threshold. If one variable falls short, the others must rise dramatically to compensate. The sun has the luxury of gravity. It uses immense density and stable conditions over billions of years to make fusion inevitable. We do not have that luxury. On Earth, we must compensate for our lack of gravity with brute force engineering. This has created two rival schools of thought. One tries to trap the star in a magnetic cage to maximize time, the tokamak. The other tries to crush the fuel with lasers to maximize density, inertial confinement. But regardless of the method, every single machine faces the same initial enemy. Before we can worry about magnets or lasers, we have to overcome the fundamental force that keeps the universe stable. Our journey begins not in a modern laboratory, but in the freezing darkness of the primordial cosmos 13.8 billion years ago. Two protons don't naturally come together. Their positive charges force them apart. Imagine the universe shortly after the Big Bang. It was a vast, cooling fog of hydrogen. In this primordial darkness, a fundamental conflict shaped the cosmos, gravity pulling matter inward and electromagnetism pushing charged particles apart. Gravity wanted to pull matter together to form stars, but electromagnetism had a different plan. At the heart of every hydrogen atom sits a proton, a positively charged nucleus. According to the laws of classical physics, if you try to push two positive charges together, they repel. This is the Coulomb force. It's like trying to push two strong magnets with the same poles together, but at the subatomic scale, this repulsion is a staggering barrier. It acts like an impenetrable barrier, a quantum jail that keeps atomic nuclei separated. If the universe operated solely on classical mechanics, this story would end here. The repulsive force would be too strong. Hydrogen clouds would compress heat up, but never ignite. The universe would remain dark and inert, filled with cold gas, but no stars. But the universe has a cheat code: quantum tunneling. In the bizarre world of quantum mechanics, a proton is not just a solid particle. It is also a probability wave. Its position is not fixed. This fuzziness means that occasionally, very occasionally, a proton can simply tunnel through the Coulomb barrier as if the wall wasn't there. It doesn't climb the energy hill, it tunnels through it. This quantum probability is the only reason the lights turned on. It is the spark of creation. The sun wins this war using the one weapon: we do not have time. Inside the core of our sun, the density is crushing 150 times that of water, and the temperature sits at 15 million degrees Celsius. Yet even in this hellish environment, fusion is incredibly inefficient. The probability of any specific proton tunneling through the barrier is so low that on average, a single proton will bounce around for 9 billion years before it successfully fuses with another. The sun shines only because it is massive. It compensates for the terrible odds with sheer volume. It is essentially a colossal, slow-burning fusion furnace that survives because it has an endless supply of fuel and billions of years to burn it. We do not have billions of years. We do not have the gravity of a star. We need energy today, not in an eon. To make fusion viable on Earth, we cannot rely on the sun's lazy pace. We have to accelerate the reaction rate by orders of magnitude. We have to force the probability window, the gamma window, wide open. Since we cannot replicate the sun's gravity, we must compensate by drastically increasing the temperature T. We have to push the fuel particles so fast that their kinetic energy overrides their electrostatic repulsion. The math is brutal. To achieve a functional reaction rate on Earth 15 million degrees is not enough. We need to go 10 times hotter. We need 150 million degrees Celsius. At this temperature, matter ceases to exist as solid, liquid, or gas. Electrons are stripped from their nuclei, creating a roiling soup of charged particles called plasma. This is the fourth state of matter, the substance of stars. But creating a substance hotter than the core of the sun on the surface of a rocky planet presents an immediate, catastrophic engineering problem. There is no material in existence, no steel, no tungsten, no diamond that can hold 150 million degrees without instantly vaporizing. We have figured out how to create the fire. Now we have to figure out how to build the fireplace. You cannot build a furnace out of steel to hold a fire of 150 million degrees. At that temperature, any solid wall would vaporize instantly. If physical walls are impossible, we must build a cage out of something immaterial. We must build a cage out of force. This brings us to the second variable of the Lawson Criterion confinement time tau. We have the heat T, but now we need to keep that heat from escaping long enough for the nuclei to find each other and fuse. Fortunately, plasma has a distinct weakness. It is electrically charged, and because it is charged, it is enslaved by the laws of electromagnetism. When a charged particle moves through a magnetic field, it experiences the Lorentz force. Instead of flying in a straight line, it is forced to spiral tightly around the magnetic field lines, like a bead sliding along a string. If you shape these magnetic strings into a closed loop, a donut shape known as a torus, the superheated plasma will race around in endless circles, never touching the walls. This is the principle behind the tokamak, a Soviet design whose name comes from Russian. Inside this machine, massive superconducting magnets cooled to near absolute zero, minus 269 degrees Celsius, generate a magnetic field tens of thousands of times stronger than the Earth's. Inside the vacuum vessel just meters away, the plasma rages at 150 million degrees. This creates one of the most extreme temperature gradients ever engineered. But trapping a star is not like trapping gas in a tank. Plasma is a fluid that conducts electricity, which means it generates its own magnetic fields. It fights back. Imagine trying to hold a sphere of trembling jelly together, using only rubber bands. As you squeeze, the jelly bulges between the bands. The plasma twists kinks and writhes, desperate to escape its magnetic prison. These instabilities can cause the plasma to crash into the walls, a disruption that instantly cools the reaction and can damage the machine. For decades, the fight for fusion was a fight to keep the jelly inside the rubber bands for more than a fraction of a second. By the late 1960s, Western fusion research was hitting a dead end. If the Soviet results were wrong, magnetic confinement would have faced a major setback. The 1950s and 60s were an era of frustration. American machines like the Stellarator and British machines like Zeta were leaking plasma like sieves. They couldn't keep the fuel hot enough long enough. The physics seemed broken. Then in 1968, at a conference in Novosibirsk, Siberia, Soviet physicists dropped a bombshell. They claimed their machine, the tokamak T3, had achieved electron temperatures of 10 million degrees, approximately 1 kilo electron volt, and confinement times far exceeding anything in the West. The claim was so outrageous that Western scientists assumed it was a measurement error. In the paranoid atmosphere of the Cold War, skepticism was the default setting. The Soviets, they reasoned, were misinterpreting the data. But in an unprecedented move of scientific diplomacy, the head of the Soviet program invited a team of British physicists from the Coulomb laboratory to come to Siberia and check the math themselves. The British team, later nicknamed the Coulomb 5, arrived carrying 5 tons of specialized equipment. They brought a diagnostic tool the West trusted: laser Thomson scattering. Until then, temperature was measured indirectly, but Thomson scattering was like a radar gun for particles. By firing a ruby laser into the plasma, the British scientists could analyze how the light scattered off the electrons. The shift in the light's wavelength, the Doppler shift, would give an irrefutable measurement of the electron's speed and therefore their temperature. For months, they worked in the heart of the Soviet Union, calibrating their lasers under the watchful eyes of their hosts. The tension was palpable. If the measurement failed, the tokamak was a fraud. Then came the results. The laser didn't lie. The temperature wasn't just high, it was exactly what the Soviets claimed. The T3 had successfully trapped the hottest plasma on Earth. The result sent a shockwave through the scientific world. Within a few years, tokamaks became the dominant path, and many Western programs pivoted toward the design. The T3 became the blueprint for the future, the grandfather of the colossal ITER reactor, currently being built in France. The laser had saved the magnetic bottle. But across the ocean, American scientists looked at the laser and saw something else. They didn't want to use it to measure the plasma. They wanted to use it to create the plasma. They decided to stop fighting for time and start a war for density. If you cannot hold the plasma in a cage for seconds, there is only one option left. You must crush it before it can escape. While the tokamak builders were fighting for time tau, trying to keep a plasma stable for seconds and eventually for much longer, another faction of physicists decided to attack the third variable of the Lawson Criterion, density n. They argued that you don't need to sustain the reaction. You just need to create conditions so extreme, so dense, that the fuel burns in an instant on the scale of nanoseconds. This approach is called inertial confinement fusion, or ICF. It is not a marathon. It is a violent sprint. The cathedral of this approach is the National Ignition Facility, or NIF, in California. It is a building the size of 3 football fields, designed to do one thing: focus 192 of the world's most powerful lasers onto a target the size of a peppercorn. The target is a masterpiece of precision engineering, a tiny capsule often made from advanced plastic filled with frozen deuterium and tritium. But the lasers do not shoot the capsule directly. Instead, they fire into a small gold cylinder called a Coulomb that holds the capsule. When the lasers strike the inner walls of the gold cylinder, they vaporize the metal, generating a bath of intense X-rays. These X-rays roast the outer surface of the fuel capsule, causing it to explode outward. According to Newton's third law, for every action, there is an equal and opposite reaction. As the outer shell blasts outward, the inner core is driven inward. This is the rocket effect. It creates an implosion of terrifying speed. The fuel collapses inward at nearly 400 kilometers per second. For a brief moment, the density of the fuel skyrockets. It reaches extreme densities far beyond anything found in ordinary materials. The pressure at the core spikes to billions of atmospheres. It is essentially a laboratory-scale supernova. The goal is to compress the fuel so fast that its own inertia keeps it together just long enough for the fusion reaction to ignite and burn through the pellet before it blows itself apart. But this method requires a synchronization of godlike precision. All 192 laser beams must arrive within an unimaginably tight timing window on the scale of picoseconds of each other. If the compression is slightly uneven, if the sphere is squeezed into a pancake or a sausage instead of a perfect point, the fusion fire fails to light. For decades, the NIF was criticized as a failure, a machine that promised the sun but delivered only expensive data. Until December 5, 2022, at 1:03 a.m., the NIF fired a shot that changed history. The lasers delivered 2.05 megajoules MJ of energy to the target. In the blinding flash that followed, the fusing hydrogen atoms released 3.15 megajoules of energy. For the first time in the history of controlled fusion, more energy came out of the plasma than the laser energy put into it. The gain Q was greater than 1. This is the definition of scientific ignition. The headlines screamed that the energy crisis was solved, but headlines rarely understand engineering. While the physics was a triumph, the engineering reality is sobering. This is where we face the wall plug efficiency trap. Yes, the plasma produced 3.15 megajoules compared to the 2.05 megajoules of laser light, but lasers are notoriously inefficient. To generate that 2.05 megajoules beam of light, the NF had to draw roughly 300 megajoules of electricity from the grid. In energy terms, we spent roughly 300 megajoules of electricity to get about 3 megajoules back from fusion, a massive net loss. Furthermore, a commercial power plant needs a heartbeat. It can't fire only occasionally like the NIF. To provide baseload power to a city, a laser fusion plant would need to drop a fuel pellet tracket with lasers fire and clear the debris roughly 10 times per second. It needs a repetition rate of 10 Hz. Currently, we are nowhere near that capability. The NIF proved that the physics of the stars works on Earth. It proved that the Lawson Criterion can be beaten with density. But turning a scientific experiment into a power plant requires bridging a chasm of efficiency that we are only just beginning to map. And even if we solve the wall plug efficiency, even if we build high-efficiency lasers and perfect superconducting magnets, there is one final boss waiting at the end of the level. It is an enemy that doesn't care about heat or density. It attacks the very structure of the machine itself. We worry about the plasma melting the reactor, but heat is not the machine killer. The real threat is invisible, chargeless, and relentless. When deuterium and tritium fuse, they produce two things: a helium nucleus, also called an alpha particle, and a high-energy neutron. The helium nucleus carries an electric charge. This is good news. Because it is charged, it remains trapped by the magnetic field, transferring its energy back into the plasma to keep it hot. It is the self-heating mechanism of the star. But the neutron carries no charge. To a magnetic field, it is effectively invisible. Born with a staggering kinetic energy of 14.1 mega-electron volts, it ignores the magnetic cage entirely. It flies straight out of the plasma at roughly 5% of the speed of light and slams directly into the physical walls of the reactor, the first wall. To understand the violence of this event, we must look at the atomic scale. In typical fission reactors, fast neutrons are on the order of a few mega-electron volts. In a fusion reactor, they are 7 times more energetic. When a 14.1 mega-electron volt neutron strikes a tungsten or steel atom in the wall, it doesn't just heat it up. It transfers enough energy to displace atoms from their lattice sites, damaging the crystal structure. It knocks the metal atom out of its secure position, sending it careening through the crystal structure like a billiard ball smashing into other atoms. Materials scientists measure this destruction in a unit called dPa, displacements per atom. In a commercial fusion power plant, the neutron flux will be so intense that every single atom in the steel wall will be knocked out of its position dozens of times during the reactor's operational life. This constant atomic reshuffling leads to embrittlement. The metal loses its ductility. It becomes brittle, prone to cracking. It leads to swelling. The accumulation of helium produced by nuclear reactions inside the metal creates microscopic bubbles, causing the reactor walls to literally puff up and deform. And finally, it leads to transmutation. The neutrons change the atomic identity of the wall, materials turning stable elements into radioactive isotopes. This is the nightmare of fusion engineering. We are trying to build a machine that must last for decades, while subjecting it to an environment that shreds materials at the atomic level. It is like trying to build a fireplace that is constantly being hammered by high-energy neutrons. The neutron is a curse because it destroys the machine, but it is also our only hope because without it, we have no fuel. This brings us to the final silent crisis of fusion, the fuel supply. The deuterium part of the fuel is easy. It is found in seawater. Seawater contains vast amounts of deuterium, enough to power civilization for a very long time. The tritium part, however, is one of the rarest substances on Earth. Tritium is a radioactive isotope of hydrogen with a half-life of only 12.3 years. It decays so fast that nature does not keep it in stock. The current global inventory of commercially available tritium, mostly harvested as a byproduct from CANDU fission reactors, is estimated to be less than 30 kilograms. That's the scale of the supply problem. A single commercial fusion power plant would burn through tens of kilograms of tritium every year. If fusion scaled up without breeding, the tritium supply would become a hard limit almost immediately. So where do we get more? We cannot mine it, we have to breed it. This is where the neutron paradox comes into play. We must turn the reactor walls, the very walls being damaged by neutrons, into a fuel factory. Engineers propose lining the reactor with a breeding blanket containing lithium. When a stray neutron strikes a lithium-6 atom, a nuclear reaction occurs. Lithium-6 plus a neutron yields tritium and helium-4. The lithium absorbs the neutron and splits, creating helium and tritium. The engineering challenge here is razor thin. We need a tritium breeding ratio greater than 1. This means for every neutron produced in the plasma, we must catch it and produce at least one new atom of tritium to replace the fuel we just burned. If the ratio drops below 1, if we lose too many neutrons to structural steel or gaps in the armor, the reactor runs out of fuel and cannot operate sustainably. We are currently building massive particle accelerators like the IFM-IFDONES project in Europe specifically to bombard materials with high-energy neutrons, simulating the hellscape of a fusion reactor. We need to find materials that can survive the irradiation while simultaneously breeding the fuel to keep the star alive. This is the final test of the great filter. It is not enough to create the spark physics. It is not enough to hold the spark confinement. We must build a vessel that can feed itself and endure the fire without burning down. Every new record lasts only a few seconds, but those seconds are history in the making. It is easy to be cynical. There is an old joke that fusion is 30 years away and always will be. But cynicism ignores the trajectory. In the early days, confinement times were measured in tiny fractions of a second. In the 90s, the jet reactor in Europe held it for seconds. Today, machines like South Korea's K-Star and China's East are maintaining high confinement plasma's H mode for tens of seconds, even minutes, at temperatures that would vaporize a spaceship. We are inching our way up the steep slope of the Lawson Criterion. We are solving the variables one by one. And in the south of France, the giant ITER, the most complex machine ever designed by our species, is slowly rising from the ground to integrate all these lessons into one final proof of concept. The question is no longer, is it possible? The question is, will we survive long enough to finish it? This brings us back to the silence of the night sky. Perhaps the great filter is real. Perhaps the transition from a Type 0 civilization burning dead plants to a Type 1 civilization mastering planetary energy is the hardest test in the universe. It is a race between our technological ability to destroy the biosphere and our engineering ability to save it. Fusion is our plan A. There is no plan B that scales to the stars. Wind and solar are crucial for now, but they cannot power a warp drive or terraform Mars. Only the fire of the stars can take us to the stars. We are currently the species standing at the foot of the wall, looking up. The challenge of the Coulomb barrier, the heat, the pressure, and the neutrons, is not a punishment. It is the tuition fee for joining the cosmic neighborhood. The universe is silent because it is waiting for a sound loud enough to echo across the ages. It is waiting for us to light the match.